overcurrent relay, and specifically overcurrent relay is very versatile. And we know in the protection perspective, power system protection perspective, we discuss also that whenever a short circuit fault happens to be there, fault current is expected to be very high. So then the overcurrent principle currently we have will be applied. It is very generic, pretty old, pretty reliable, and is functioning from the inception of power system in different principles, including we talk about also fuse also. So then what we see that I was telling the other day also that there are numerous forms of relays. We talk about overcurrent, we talk about today we'll talk about differential. Also I talk about transmission line protection, distance relay, directional relay also we'll discuss, and so. So the sole purpose of the availability of varieties of relays or principles is that they are good for something, and they have their own limitations, and so. So someone may be very good in something, and so. Now overcurrent relay, as you see, that we take only the current signals, duty, at one place, and then make a judgment that whether there is a fault in the assigned element, that section or so, and accordingly the corresponding relay takes a decision to open that breaker associated with that. Two things we emphasize on that: it should be sensitive, that all faults should be taken care, that is about the dependability perspective. But for a fault outside that element or zone or the section, we call that assigned things also a zone also, that section or that element for which it is taking care, anything outside, the relay should remain silent. You should not trip. Either it may be a fault situation in the system or maybe overloading or any other situation. The relay otherwise should not trip. So that we talk about the security. So both should be satisfied. Unnecessary tripping is not desirable because customers will find out of supply, power supply. So with that emphasis that we always take a balance between dependability and security. Of course, more emphasis in general designs or settings perspective is given to dependability perspective. Otherwise, there will be possible damage and so and so. But then what is the problem with overcurrent? So we'll see, you can say that some of the perspective in terms of that. One is straightforward, that day also we make a judgment. So like I can tell you here also. So we talk about this two-line section. And this is, let us say, substation where I put this source. This is bus A, bus B, and bus C, and so on. So we say that in overcurrent principle, the time, setting time, the corresponding curve becomes, here you require this curve, then the higher level curve, then it further higher level curve, and so. Therefore, fault close by, we should have a more severe fault. Now, because the curve is the upper curve in the IDMT characteristics, clock setting number of times of the clock setting, talk PSM, and this is the time in second. Then we talk about the lower curve to this farthest one, then upper curve, then upper curve. So this curve may be A. Therefore, for a given fault level, the corresponding for a given fault level here, high level, the time decision time for the relay at A, RA, may be high. This is one of the limitations or demerits of, you can say that, overcurrent coordination perspective and so. The other one, if these line sections, this is let us say 100 meter or 500 or 200 meter, and this is let us say 100 meter. Now a fault here or a fault here, F1 and F2. These two sections, you can say that when I say fault here or here, so then fault here or fault here. The level of current for these two faults is very difficult to discriminate and to be discriminated by the overcurrent relay. So this relay will be in confusion whether the fault is in BC section or AB section because there is no clear demarcation. So therefore, even I told you that because any fault happens to be there over a line, it has associated with arcing, tar putting, and so the path of the soil through which returns. So that list also additional impedance in that fault path. Therefore, we cannot ensure that for a fault here, the level of current will be higher than a fault in the BC section. Then we are in problem with this relay answer. So those are limitations of, we can say, protection for with overcurrent relay, for even for the distribution system and so. Now today's discussion is not on distribution system, is on differential relay for transformer protection. Differential relay for transformer protection. So someone will say that let us say we have a transformer, and this it can be in a high voltage system. Both end sources are there, interconnected network, or in a distribution system it may be radial also. Let us say this is substation part. So now normally what happens that to the load side the current will flow, and accordingly you can say that in the primary side or the so-called primary, the supply side, substation side, the current will flow proportionate to that, and so N1 into H2, that is the governing factor for that perspective. Then what is fault? What is fault in transformer? Where we talk about a protection system. That is the first question. If there is no fault in the transformer, then absolutely there is no protection required. Now, faults are inevitable, not like overcurrent, not like overhead line, and so where the frequency of fault may be high. Fault in overhead line, tree touching, animal intervention, due to storm also the conductor falling on the ground. There are several reasons for that. But here in case of transformer, confined in a substation, filled with oil, and in a better environment and so the chance of fault is low, very rare. Who knows, in 20-30 years span also you may not find a fault. But a transformer life can be 40 years, 50 years also. They can be very good at also. Now, what are the chances of fault? But you cannot deny. Now, if a fault happens to be there, I think you can see Google and see, then it becomes a havoc. If it is not cleared quickly, because this oil is inflammable, and in the substation we have multiple transformer. Even in all to the 33 kV substation, if you go, then you file 3, 4, 33:11. Too many operational, and 3 are there. You can say that in operational continuous, and then redundant extra things are also there. And again, in addition to that, in that area we have 11 kV to, you can say that 415 volts transformers are there. So in a cluster we have several transformers. Even in the distribution system, if you think about a high voltage system with a large substation, maybe 10, 20 big transformers may be there. In addition, the equipment, other equipments also, very valuable, costly equipment will be there. Now, this inflammable oil that creates havoc unless it is being addressed quickly. It may blast just like a bomb. I think someone can Google, I think in New York City or so, transformer burning. You can see what kind of flame comes out. Very like petrol bomb or so. So that is about how to what is the reason of consider the how to, why fault should be addressed as quickly as possible. But the reason of fault is that transformer consider has windings. Each winding has insulation. The insulation depends upon this the insulation thickness or quality of insulation is decided by the voltage. But with time, this insulation degrades. Any crack or so, you can say that also will be there. Mechanically developed. So therefore, what will happen? We have high voltage, 400 kV, 765 kV, 800 kV, 1000 kV transformer also. So to manage with that situation, what happens that in addition to that, mechanical cracks or wet handling and so, transformer is exposed to the overall line, transmission line ends in the substation, and again another transmission line emanates from this. So therefore, this side also line and this side also line. Lightning will strike. So some you can say that traveling wave will get into you can say this. So therefore, the corresponding transformer windings may be exposed to the lightning. We have lightning arresters and so and so. But then still something may come or lightning arrestor may fail, then the corresponding voltage will come to the transformer. So therefore, the corresponding the insulation will be stress in terms of that, and there may be some minute punctures also. So through that path, initially maybe micro ampere current may flow. Okay? So that minor current slowly goes on increasing, damaging that part or making it further degradation that part, and then finally it results more and more current. Initially called incipient fault. Finally, this minor thing may result in a major thing, and that may result in considered a permanent fault. A permanent fault. This is what the genesis of generally fault in this one. This fault is nothing but that insulation failure. That insulation failure results in this because the conductors are around the core, and the core you can say that the steel core or so is grounded. So therefore, whenever any insulation failure, the phase conductor touches the finds a path current to the ground to this core. That is what the fault path. In with time, if you further degradation, then because this will lead to large amount of current, thermal heating, and so it may damage inside and so. Okay, unless being this, and this damage you can say that may be resulting into other phases, other windings, one winding to the other winding, and so, other phases also. Now, there may be also the bushing area, and so also you can say that may be more vulnerable in terms of that. Whatsoever, we see that transformer is also not, you cannot ensure that it will not have any fault in its lifespan and so. If fault happens to be there, then the corresponding permanent fault may be very, very large current, and whenever large current happens to be there, the winding may be damaged. Winding damage means insulation failure and so. That lead to large current means the corresponding core may be also there, and there will be unstable situations in the mechanical perspective also because of the large current associated and so. So then the big problem is transformer is that repairment. It will take a lot of time, and mobility is also difficult. We know size of the transformer. So transportation perspective and challenging. So therefore, it may take months also. So if you can avoid fault, all these things can be there. Now the point here is that someone will say that no, I'll have a spare, but spare I can crores of rupees and so. So from the investment and economic perspective, it is not always preferable in terms of that. However, if we have supporting economics in terms of economics, if we have, then you can put the redundancy also. So this, if you can address the fault in a better way, then your management perspective, from operational management perspective, it is better. So what is that? any fault happens to be there, if you can quickly address that, remove this fault, isolate this fault, we are talking about transformer fault, then it is better for the transformer. As simple as some monitoring, little maintenance also can save the transformer in terms of that. So this is about something fault in transformer. Now require, once there is a fault, we require a protection system. Then the question arises, why not fuse here also? The current becomes high, usually blown out. True. But again, as we addressed in the last class also, that when you go to the higher and higher voltage, the corresponding voltage and the level of current also both become very high, and the interrupting capability of fuse becomes limitation. So therefore, like after 1 MVA or so, you can say that when 2.5 MVA, 3 MVA, there is no something like that. It depends on the utility and so. So in that case, the transformer switches over to breaker and relay arrangement. Circuit breaker plus relay arrangement. Okay. So if that is so, then we talk about relay here. Circuit breaker is that again SF6, air, vacuum, and so depending upon the level of voltage and the capacity of braking we require for that particular specific transformer. In that relay, the relay commands the breaker whenever finds an internal fault. It is an internal fault of the transformer. So let us say this is your input and this is your transformer and these are output terminals. Consider single phase. Any internal faults, the corresponding relay should open the breaker. Any external fault or no fault situation, the relay should remain silent. Okay? Fine. Now there is a proposition here you can think about, that if this is so, can I put overcurrent relay? Can I put overcurrent relay? Yes. Because any internal fault happens to be there, current will be high. You can say that any internal fault happens to be there, and current will be high. Very true. So we can use, you can say that overcurrent relay, and overcurrent relay is being used for, you can say that in that sense, consider for the transformer. But again, that has a limitation in terms of that. So we see that if a transformer happens to be there, and let us say we are feeding from the substation to the transformer from this. So any internal fault, this is load side. So any internal fault happens to be there, current will be high. Fault current will be high. So that is much higher than the rated current. So an overcurrent relay will be able to detect this, and it can command the corresponding breaker here. It can command the corresponding breaker here, be open. But see a situation. This is a distribution line, you can say that, from which it emanates. So this line will be there. So here you can say that there will be another set of protection. Another relay will be there. So this relay, you can say that, takes care of this fault here and fault here. This relay will find difficulty to discriminate whether the fault is here or fault is here. This relay will find difficulty. So there are reasons like that. Therefore, overcurrent relay also finds limitation. But however, from economic perspective, overcurrent relay also good enough in many cases, up to 2.5 or MVA also, you can say that 3 MVA or even 5 MVA also. Many, you can say, the utilities will use overcurrent relay for that purpose. Same overcurrent relay, what we have studied. Agree? You can coordinate this side and that side also and manage and so. But again, coordination between this means left hand side when we are coming, then again the core will be upper one, but transformer takes a good attention. It cannot allow against the delay here. In the overcurrent line, you may little bit that same H equals to I square RT governing things. This is open conductor, but here transformer is there, so transformer protection is pretty critical. So we cannot wait, watch, or give a longer period of time. And because if you like to coordinate, so the core for the transformer will be upper curve than this core. So therefore, again, it requires more time. That is not good in many situations and so. Okay. Now, with this limitation, we'll say today's agenda is on differential relay for transformer protection. Now, what to do? Like in last class, what is the agenda of this laboratory experiment class? What do you like to do experiment? Given an differential relay, certain characteristics, like the other day we talked about IDMT characteristics, we like to verify. Whether the characteristics of the relay, as mentioned by the vendor manufacturer, the relay is following at this moment or not, that we like to test. So that is what we are verifying. Which relay? Differential relay. There is specific name called percentage bias differential relay. We'll come to that. What is that percentage bias? What is that differential? First will come, and then we'll come to what is that percentage bias relay. So, okay. So with this background, we say that this is a transformer element, and we like to consider protect the transformer using a differential principle. We'll see this theory, background, and so, and then we have a three-phase transformer in the experimental thing. How to have the relay settings there, we'll see how to have the settings like in the overcurrent relay talk, we will learn, and then we'll take observations, verifications, and then your reporting items and so. This is the agenda of this today's business. Now, the basic difference when you say the transformer protection, what you see here is that we require essentially CT this side and CT this side. In case of your overcurrent relay, we talk about CT here only. For a phase, one CT, another phase, another CT. But here we talk about in the same phase, phase A or so, we talk about two CT here. This is CT in the so-called CT1, and this is CT2. And you connect them like this. So that a differential current flows to this. Less more. A differential current flows to this. This is a differential branch, left and right. And that's in the differential things. And what is the basic background? Now, what we'll see that we'll see we make the corresponding arrangement such that this differential current, I differential should be zero during normal situation. During normal situation, this should be zero. Ideally, we should make the corresponding CT to be such because this is transformer. But whenever there is an internal fault, this I differential will no more zero. Like straightforward, whatever current was there flowing here, proportional current was flowing here. Now no more proportionality. For an internal fault, this current becomes significantly high. This current may be there, may not be there. If you have current in feed from the right hand side also source, there will be current. If you have, we can say that this is a solid dead short circuit fault, then no current will flow in that phase from the secondary side also. So that means that there is a difference between this current, and that differential current becomes no more zero. That is the clear. This is a two-class problem: external thing or internal thing. If we identify there is the internal business, we make a trip. If it is an external business, no trip. So it is a two-class problem. Yes.
So what are CT1 and CT2?
There are two CTs, current transformers.
So like they're connected to the transformer for this purpose.
Both sides for each phase. Let us say phase A. This is. Agree?
Okay. Like on the primary side and secondary side, they're connected.
I can put like this better way. We'll come to that in more detail. This is like this transformer. So this is substation side. This source is connected. So I put a CT here. This is CT1, and this is CT2. Is it okay? This goes to the load side.
Okay.
And then this connection is like this. So we'll come to more details on that. This is the basic background. So we started with overcurrent with one CT, which gives the corresponding current information only. Whatever is through that path. Here, like here, a fault happens to be there. This CT you can say able to give the input to the power current. And again, we talk about that why do we require CT? Because we have to downscale the current to substantially low level so that this is compatible to your relay device. Relay is a fault detector. We talk about a numerical relay. So it is a numerical device. That current has to be converted to voltage plus minus 5, plus minus 10 or whatever compatible to that microprocessor, microcontroller or whatever you are using. So
Sir,
this is, yeah, please.
sir, you said that the current through the relay will be differential, but here the currents are getting added up, right? Shouldn't the
Yes.
direction one
Yes.
of the
Yeah,
the current?
I'll come to that. But don't do. Yeah, I'll come to that. We'll have more details on that. But that is what the name principle says, the differential. Agree? So what is that? Plus or minus depends upon which. It will depend upon what? As you are asking, it will depend upon plus or minus will depend upon
Direction of
tell.
like
No, plus or minus will depend upon what? The polarity of the connection of the CT. Like I can say here, if the CT is, you can say that, CT is connection, you can say that will be the other way. Put my dot here, this side, then the polarity will be reversed. So secondary, you can say that the current with this current, what I am saying will be in the other way. Okay? So one CT remaining intact, the other CT I can change also. So that is what very common issue what we address in the lab, but we don't, we are not in the lab, so what can I do? Agree? So what I like to say that, let us say in experiment what we do. So once this transformer is there, I connect CT and CT1, CT2 and connect like this. My first job is, I put some load and see that in one of the CT connections, if the corresponding differential current at that loading condition is not zero, then my polarity of the CT connection is not proper. So I don't trust the CT, I interchange the two terminals of the CT. Okay? Current in the primary of the CT will flow as usual. In the secondary now will be reverse. That is what the polarity you can say that we talk about in terms of that. Agree? Dot
yes,
dot
sir.
convention in the polarity. So it is a polarity, you call CT polarity. So once you check that, you can say that normal time the corresponding differential current is zero, then your connection is okay. That is the first check we do. Then what happens that whenever you can say that an internal fault happens to be there, then also you can check and see that you can say that the differential current flows here and differential current may not be flowing in the other side. So that you can say that this differential current is, so this side will be large current, this side will be no current. So therefore this current will be significant. That is your first check. Agree? So this is a requirement you can say that from the connection perspective and so to satisfy that one. Okay, we'll come to more on that philosophy. This is the approach you have to follow, you can say in terms of that. This plus, so that plus and minus, it depends upon like we talk about. These are all phasors. I'm talking about phasors or in that polarity perspective. So 180 degree, if it make it phasors reverse, then it becomes the other way. It's similar to that. Okay. So in this experiment, we have Schneider Electric, you can say that 8070, we call MICOM P634. This is the relay model we talk about. Schneider donated us, you can say that some 2-3 relays, and then we are using for that also. So this is the relay part. This is the relay part, and this is the relay. That is our testing part. Earlier relay, consider this is about electromagnetic relays. They are in that same panel also. If someone likes to see it, can come. Why do you do that? We have a bank of, you have transformer, we can say that three-phase transformer, three-phase in 1 kVA each. I believe, yes, 1 kVA each, you can say that transformers are there. Bank of transformer, this side. And then we have some loads here also. And these are, you can say that some rheostats, you can say that we have specific region. I will tell you while going for the experimental expansion. And these, you can say that bulbs are a load also. Like we like to load the consider the corresponding transformer. So there are additional load here also consider, but the 100-watt bulbs are the loads for the transformer also. So this transformer, you can say that terminals are connected to the through the CTs. To the CTs for each page is connected to this. we talk about that. This is a three-phase transformer arrangement, and this is a three-phase relay for that perspective and all these things. But this relay it's being used considered in the system, large scale voltage and so compatible with that. Fine. So coming to our principles on transformer differential principle and so. So we are, you can say that we are in the process of, you can say that process of description of the differential principle, and then we'll go to consider 40% differential principle. So one by one. So we talk about transformer differential. So this is what the basic perspective of a differential thing. Any element, transformer or whatever, this differential principle is extended to the most powerful, you can say that we can say principle on protection on relaying principle, very good at. But it has also, you see here that we require information from both these sides. So we can extend it to consider that we'll tell towards the end, also to the transmission line also, distribution line also, and so. So this element can be anything. So you can say this side current, and if my polarity of the city is such that this is the positive forward-looking direction for this side city, and this is the forward-looking direction for this side. So I1 plus I2, if we apply KCL, you can say that I should be 0 normally. But whenever there is an internal fault, this current and this current will not be same. If source is to the left and there is no source, as I told you earlier slide also, then these two currents will not be same. So therefore, KCL will consider give a non-zero value. That is the basic philosophy of differential principle. So that's the part. Now we see to the transformer here. So let us say this is single phase transformer. We can extend to three phase like this. The main transformer turns ratio N1 is to N2. And then we have a CT here which is having 1 is to N1, 1 is to N2. So what the 1 means? Primary side 1 directly, and on the that primary conductor, you can say that the line side, this is the line side of the transformer. Line side, we own the corresponding things. So the secondary has been number of turns. So the number of turns, we can say that voltage is up, current is small. That is the principle. So that's why we talk about that CT should not be kept open also. If the CT secondary is kept open, then the corresponding voltage becomes enormously high, and that will be detrimental to the system and so very high voltage. Because if you are scaling out 1000:1, 3000:1, also CT also there also you can say that. So therefore, accordingly corresponding turns ratio will be decided. Now, these currents are fed to the corresponding, they are connected like this as here. This is called differential connection. And in the differential branch, we have this relay. As I said, the principle is differential relay. That difference current we want to notice, yes, significant, non-significant. So what we see here, that in this case, how the corresponding relations holds good, and what kind of CT ratio we should select also, that we like to do as I mentioned. Now we know, we can say that from this ampere turn balance, from the ampere turn balancing, so N1 and N1 I1 equals to N2 I2. This is in the primary side, about this side and this side. This primary, P for small p for primary, S for, you can say, secondary. So secondary means CT secondary current is being fed to the relay. That secondary current is smaller current, but primary current can be substantially high, can be in kiloampere and so also. Now this I1P, like this side, this I1P can be expressed in terms of I1S using this 1:N1, and that is what you can say now. If you substitute the corresponding I1P into N1 into I1S, and I2P you can say N2 into I2S, then we say, you can say that this ampere turn relations happens to be there. Now what is our target here? The differential current which we are talking about is I1 plus I2S as per this connection. So this will be I1 plus I2S. So this should be 0. When? Normally, that is our target. How can it be? Now if we say in this condition that if N1 N1 equals to N2 N2, then this can be achieved in terms of that. Is it not? If N1 N1 equals to N2 N2, left hand side will be equal to right hand side, and our connection should be such that you can say that they should be opposite to each other in this branch during normal condition. I told you from the very beginning, that is my check, that I should connect secondary some load and see that you can say that the polarity of the cities are connected such that during normal situation, differential current is 0. And this 0 can be achieved if you select the corresponding pole, city ratio will be there. Now, what kind of city ratio will be there? No, that depends upon the transformer turns ratio. But this N1 equals to N2 into is a theory thing. But practically, 33 is to 11 kV, 11 kV is to 415 volt, 220 kV is to 33 kV. These are all transformations talk about the voltages. So for that case, this so-called this small N1 by N2, I'm bringing this equals to N2 by N1. So this ratio, so whatever N2 by N1 have, accordingly you can say that this N1 by N2 will be there. Now what happens, however, in market or the manufacturers, they don't provide, you can say, this kind of transformer, this kind of CT, you can say that for you. This is for the CT, this is for the main transformer. So transformer is there, but the CT will be available in terms of 100 is to 5 or 1 ampere, 5 ampere or 1 ampere, 1000 is to 5, 600 is to, you can say that 5 or 1 ampere or so. So these kind of standard cities are there. So the ratio of cities are very standardized. You can see Google and see any from the manufacturers what they provide. And cities will be several in numbers, you can say that in this system to be connected and so. So therefore, what happened that this is not always possible also. But what is our target? We should do as close as possible in that perspective. Agree? So I told you here that what is theory, what is availability in the system perspective. So there is a chance that in actuality there will be a mismatch. Once you have a mismatch, what will happen? Once you have a mismatch, so during normal time also, this current is no more 0. Yes, that we call spill current. That we call spill current. So therefore, that spill current is not a fault situation. It means that for a fault judgment, we must address that spill current. That our fault, this is, you can say that our so-called IP curve, that we were talking about, I setting, should be above this one. And what is that? This kind of issues. This is one of the issues, you can say that. Okay, you understand from this one. Now, two things happened here, which may confuse the relay, or which is the target. Like in overcurrent relay, we talk about internal fault, external fault beyond the line. Beyond the line, the relay should not treat depth, dependability, and security. This is differential protection. So first we are addressing internal fault. Internal to what? To the transformer. Now what is we call internal in this sense? No, it may not be in the transformer. Because who is taking that judgment? The relay is taking the judgment. Yes. Now the relay is taking judgment through what? Getting the signal from the city. Getting signal from the city. So now who has the city? This is one city, this is another city. So the zones of protection or this section to which this relay is taking care for protection and the associated breaker to which it will trip is nothing far from this to this. So transformer, the allied connections from here to here is taken care by this relay and the protection arrangement. Really? Anything happens here. Here a fault happens to be there, here a fault, or inside the transformer also. Winding, bushing, wherever it happens to be there. True. So the point here is that is what internal to the system. And what is external? Anything beyond these two cities, anything beyond these two cities, these are our sensors, we will call external. Anything happens here is an external. So now the question is that during external, the differential current should be 0. Ideally, during internal, the differential current will be substantially high. So in this case, as I already mentioned earlier also, the arrangement of, we can say that this city polarity connections is such that this is for internal. So for internal case, you can say that we talk about the connection, you can say that is forward looking, you can say that the cities are connected such that in this case, the corresponding current becomes I1 plus I2. So So internal fault, and this becomes non-zero, substantially high. Now come to consider, if we compare to this external fault loading condition, so this is external fault condition. We will compare it left and right, internal versus external. So now what will happen? If you see here, from this side, let us say substation side, this is source side here, the current is flowing like this. So there is no change in current in here. But for this side, for internal fault, current will, if there is source this side, current will flow from right to left, or this current can be substantially low or zero. Could you follow me? Now, if you see here, this current, because source is this side, so this current will same as this. So therefore, this is also downward, this is also downward current. But to the right hand side here, this current is going away, unlike here. So therefore, the corresponding current is reversed now. Not this way, it will be this way. Reverse. Reverse means this side. This side. So now at this point, if you see this, you can say that where you can say we can apply the KCL. So current is coming here and also current is coming here. So these two are added as per this convention. Same convention we have put here. In the external fault case, the current is coming here and the current is going away from here. And if these two currents are same, then I operating becomes zero. When they will be same, as I told, N1 equals to N2 N2. Assuming this current will be zero. That is what internal fault versus external fault. Okay? And that is what normal differential principle we say. Now, this is a convention. There are other way also. Some of the things you can say. This becomes minus sign also put also. Don't confuse. But philosophy is that same one. Okay? So plus minus for the protection convention and all these things. It doesn't matter how the phase relation happens to be there. That matters to us. Now the question you can see that here. You can see that what is this relay here? What is the relay
Sir?
here? Yes, please.
Sir, you said that in normal conditions, my differential current will be zero, right? When there is no fault. Now, like in external fault case also, my differential current is zero. So, like, how will you understand whether there is fault or not, or it is normal operating condition?
Very right. You are able to judge, you can say that internal fault. True, because differential current is significant. So it will above a threshold or so. Simply in terms of the current perspective. So then you can say that internal fault is clearly identified. Your question that external fault you don't know. It is not possible. Not required. Why not required? This relay setup is to take care of this transformer. This umbrella is to take care of my head only. Really, I don't bother about what others are happening. So this is that philosophy here. What you are saying that this differential principle has a limitation. Very rightly pointed out. This differential relay principle has a limitation. What is the limitation? In the overcurrent relay here, you talk about that any fault here, this overcurrent relay can see and make a judgment at a later time. That is what the coordination. In the last class you understand. Now suppose you can say that I put a differential principle here for this line. I put this connection like this. And then this is my differential branch current. Roughly. Any fault here, you can say this differential current will not know. Zero current. So this is the limitation of differential principle. Any external thing, any external fault, it cannot put a backup also. Very true. It cannot provide a backup also. Another demerit from the beginning, I'm telling you, this is required for a line, a communication. The corresponding signal has to be brought to some place, this end or that end or anywhere. If there is a communication link failure, then there is a problem. These are the limitations of so any system, any principle you tell, there is a pros and cons. What you say is correct. This relay will not be able to identify external fault. But from the protection principle, that is not a requirement also. That is not a requirement. From backup principle, if this breaker fails somewhere here, then the following things will not be a problem. That is a generic problem in terms of that. Okay. Now
So,
the mic. Yes.
So, why are we assuming the current of the secondary to be from right to left in the internal fault condition? and like left to right in the
We are not considering anything. This is not my consideration. And so from the very beginning, I told you, let me clear you. Sorry. So very beginning, you mentioned about, you can say that I'll connect this corresponding city such that during normal time, what you do with that, let us say this is transformer. I think I can elaborate you. I think perhaps here. This is the transformer, and this is the load, and this is city here, and this is city here. This is source side, substation side, supply side. This is city here. So this is my city 1 and city 2 or so. So what I connect like this. And this is the differential branch we'll talk about here. Now what we do is that what I say here, I'll check the city connection such that during loading condition this current should be 0. So what is this current? What is this current? As per my convention, this. So I said that. So that's why I told that whenever normal condition or any external fault condition, this current will be 0. So the polarity, what I did that if this is not showing 0, I made the corresponding interchange the terminal of the consider the corresponding city in the primary side. Agree? The primary side, 2 terminals, 4 terminals will be there. Primary terminals and secondary terminals. So this you can say that I interchange this one. So the connection is reverse. This will be connection to the relay as it is. So once I interchange this, then my polarity can say change. So that will happen. That normal time this will be 0. Now any internal fault happens to be there. This current is substantially high. This current will be negligible, small, or whatever. Or if there is source this side, this current will also reversed. So that's why we say that this current will be now in this case, if there will be a reversal of current for this internal fault or so, then the corresponding current will be more 0. Could you follow now? Current was flowing here to here. Now for let us say both end sources are current will flow from here to here now. This current remaining same. 180 out of phase. So whatever you can say that differential relay set up the corresponding this equals to 0 I took, no more that will be 0. That I set first. That is what the polarity connection of the cities. That I ensure. Then I am talking about this. Once I do this, you see here, once I do this, what I like to say here, that in this case, the current you can say that is flowing from right to left to right. But here in this case, same arrangement. Here this current is flowing to left to right, same as this. But here this is change. This again you can say flowing from left to right. Like here, right to left. That's the difference. Okay? So then, therefore, in this branch, you can say that when I told you, consider this is flowing from this to here, and this you can say that is coming from here to here. So I apply KCL, you can say that becomes plus. But here you can say if I say it is going here and going out of this. But these two currents are same theoretically with N1 and N1 equals to N2 N2. Then this operating current will be 0. This branch, if I apply, I can say KCL, this will be 0. Okay? Now, our question you can say that was that what should be the corresponding current here? What should be corresponding relay here? Which relay I should pick up now? This R means what? Is it overcurrent? Is it something that you like to say? Okay, so that point we have come to now. That what is that R here stands for? So this is that relay we are talking about, which needs a connection like this, and that relay called a differential relay. But as we say here, if I put a threshold, some spill current and so city ratio mismatch and so, or any something mismatching in the connections and so and so. Some threshold, that is my I threshold, current I pick up. If it is something greater than this is a trip. If it is not greater than this you can say it is a block region or restraint region we call it. Okay. So this is the principle I can do. So this relay can be considered nothing but an overcurrent relay. Overcurrent is one word. So this is an overcurrent, over voltage, under voltage. This is one word, single word. So this is a very good principle. This is a very good principle, which what you can say that on the principle also called differential. Okay, so what we say, but this has certain issues. What are the issues? Same incident arrangement we are talking about. What are the issues? Now, the point here you can say that is that I'm taking two, you can say that this plot here. One is called I restraint, and this is called I operating. What is operating? The corresponding this one, I1 S plus I2S. Secondary current addition. This branch current is operating current. So earlier our thought was the overcurrent principle. If the current in that I operating instantaneous or phasor, let us say phasor we are talking about, I operating is greater than I threshold, this is trip. This is trip. But what happens? As I say, CT mismatch. What is CT mismatch? What is CT mismatch? N1, N1 is no more, you can say that N2, N2. What will happen? As I said, that this side, at the normal situation also, one side current may be higher than the other one. So the differential current will be no more zero. So there will be a current here. So depending upon the mismatch, this field current will be there. Through current or field current will be there. Now, that is not the only thing. You know, you can say that CT is a magnetic, having a magnetic core. So it will saturate. CT will saturate. But this side CT is not same as this side CT. So saturation of one and saturation of other, they are independent. So one may saturate, the other may not saturate. Both may saturate. Fine. Now let us say assume that one saturation. So one saturation means what will happen? Now if there will be saturation, so normally you can say this is the current, let us say. So in case of saturation, let us say deep saturation, what signal I am just for clarity, you can say I am talking about. So deep saturation, the current will follow like this, and maybe like this and like this. So this current, the blue curve, actual current in the fault system side is the red one, and the blue curve we can say is the CT output secondary side. After scaling, both are plotted in the scale. Agree? Normalizing or after the making, you can say that referring to secondary both side. So this is about the saturation situation. However, in the primary this side, the saturation may not occur. So external thing it happens to there, and this saturation, this CT has saturated like this and giving me a secondary current like this. But this primary side, this side, other side is having proportionate current. So this side current, this current for this external fault will no more matching, and there will be significant current flowing through this differential branch. Now, if you apply this principle, then this will trip, which is not a fault. This is a common problem with CT saturation. Furthermore, now the transformer has tape changing transformer. You know, high voltage side have tape changers to adjust the voltage in the output voltage, so that the customers get or the network gets considered very reliable up to the within that plus minus 5% voltage and so. To have a very stringent voltage regulation, we have, we can say that tape changing transformer. What do you mean by tape changing transformer? In tape changing transformer, the N1 is to N2 ratio changes. Automatic. On-load tape changing transformer, under-load tape changing transformer, there are different names. So if the tape changing transformer is functioning, then your N1 equals to N2 will no more valid. Continuously changing, or depending upon the loading condition and the voltage profile of the voltage situation of that system. So that means that there will be always some spill current through this. We'll take care of that. If you do that, someone will say that no, I'll manage with the overcurrent. And what will happen? The overcurrent setting of this level will no more valid. The overcurrent setting may be higher and higher. So your ITS threshold value more and more. What will happen? A fault in the transformer, I'm putting inside that for clarity. See here, what happens with the fault in the transformer? A fault in the transformer, let us say, if a fault happens to be towards the lower of the winding, the voltage associated is smaller. The current to the fault path will be smaller. If the fault happens to be in the upper portion of the winding towards the input side, then the path, you can say that through this will be very limited one and the current will be very, very large. So the lower level of current may not be detected by this threshold because it may be lower than this also. Because you can say that the differential current, as I was trying to point out for internal fault, for any internal fault, the differential current is this side current plus this side current. For internal fault, this current, let us say this side current may not be flowing because it is a dead short circuit. So this side current will flow. So the corresponding fault current, which is going from this to this, let us say this side current is 0, this side current is there. So this current is nothing but proportional to this current. So the differential branch current is same as the proportionate to that as the fault current. Always. The differential branch current is always proportional to the internal fault current because of the CT ratio and all these things. So that's my point, is that in case of fault towards the end of the, you can say that transformer winding, the associated current may not be significant, and in that case you can say that our judgment on what threshold value will take will lead to issue. The relay must take care, you can say that this part also. That is a requirement. So from this perspective, we say that overcurrent has a limitation in terms of that. And then you can say that we are talking about what should we do. So therefore here we have a plot here, you can say that in terms of that we talk about, we'll switch over to some other characteristics, and that is what it's called the differential characteristics or percentage by differential. This is differential current, simple overcurrent, differential principle, called earlier it was called March price principle or so and so. Forget about that. We have differential principle, but the differential current is not the only indicative of that. Is not adequate, you can say, to address our requirement, because we talk about selectivity, dependability, security, and all these things. So we require something better. Now, what is that better? So what do you do that? We call I restraining. As I mentioned, we call I restraining current. I restraining or restrained current. This I restraining current is called also through current, proportional to through current. What is through current? Current through this and through this is going away. Agree? So during external fault condition, this is through current perspective. Now come to consider that operating current. This is the operating current is through the relay. The differential current operating through the relay. Now this operating current versus restraining current. Now what is the situations we see here? 2-3 things which I talked about that if you apply the corresponding transformer here, any transformer here, so no load, you energize, magnetizing current will flow 2%, 3%, whatever may be. 2. So this is about the magnetizing current for a enter line. Whatever this operating current, whatever the restraining current, this is for a on this plane, it will be for a enter current. Now see here, we have CT ratio and tape changer, that N1, N1, N2, N2 mismatch. Now what will happen? The more this current, external current, see here, the more the external current through current, that is just through current, the more the restraining current. Agree? What is taken, I'll tell you, can say in our subsequent slides. More is the restraining current because this is reflecting through current, the external current. Now this, if the corresponding external current is more, then the CT I1 is to I2 equals to N2 is to N1, because N2 is to N1, that ratio is not satisfying need now. So therefore the mismatch, you can say that in this part will be more and more. This is what the line.
Sir,
yes.
Sir, sir, what is the through current? Like, can you say again?
Yeah. So this is you can say that the current which is flowing towards the load, going away from the transformer, and also is that current will definitely come from this side. So external fault, or it's called through fault, or external loading condition also is the through current going through both the windings. Like you can think about in our own interpretation, we can say that. So this is the equivalent impedance of the transformer, Z, leakage impedance, and so the current is flowing through this. But for internal fault, the current will be here somewhere, some percentage here, some percentage here. So the current which is flowing through the, you can say that transformer, both the windings, is called through coiled or through fault or so. That is, at that situation, the relay should not function. So that current, through current, we call through current, proportional to that the restraining current there. But the restraining current has some relation also. So that restraining current, that through current means external current is more, then the corresponding the differential current will be also more and more because of the CT ratio mismatch. If the CT ratios are there, as I told, then it will be zero anytime. But because there is a CT ratio mismatch either due to unavailability of the proper CT or tape changing transformer is changing this ratio, then this field current will be more and more if the load is more and more. Load 0, this will be 0. Load 1 ampere, small. Load 100 ampere, that will be more. That is what we like to say from these characteristics. Now the other thing I can say that is about the CT saturation. This curve is like this. You know this. CT saturation. CT saturates, one side saturates, the other side does not saturate. Both may saturate, but the saturation will be different because they have their different CT ratio and so. 100:1, someone is in high voltage side, someone in the low voltage side, and so and so. So they cannot be equal. In a transmission line, this CT and this CT is theoretically they can be same because 100:1, 100:1 will be required. But in a transformer, because of this low voltage and high voltage, current levels are different. So CT selection will be different. Like we talk about CT selection in the distribution system also, that we mention the corresponding CT ratio to their normal loading load condition, full load condition, full load decides, you can say that, what ratio of the CT will be there. So based on that, this in a transmission system or distribution system for differential protection also, CTs will be same ratio. But in case of transformer, they cannot be same. Okay, in this kind of situation. So now we'll come to consider what is that percentage bias differential protection. We find a limitation on this overcurrent pin spool or the associated differential current pin spool. That overcurrent is nothing but the difference current or differential current. So we go to consider this percentage bias differential pin spool. So this is what we'll see now, that we call a characteristic like this. So the trip condition is that the I operating should be greater than IPU. IP means this is that pickup setting, pickup current, minimum current. What is this point? Even though there is no through current, even though this corresponding restraining current is not there, then also we have this one. This is that spill current. Why this spill current? CT ratio mismatch, magnetizing current, and all these things. Even though this current is zero, through current is zero, through the, you can say that, transformer winding, no current is flowing, no load condition. Still, you can say that we have to keep something. So that's why the starting point of the characteristic is this. Then we have some horizontal line. These are not generally fault situation kind of thing. And then we have, you can say that, a line like this with a slope of m, with a slope. How to decide that slope? I told you here. So this, you can say that the combine all the, you can say, add all, you can say that these issues here. Then we add, you can say that you get a combined thing curve like this. So this is, you can say, total false current or spill current, which may cheat us, But as I said, in the transformer winding, a fault near the close of this winding, may find a point here also. That's the issue. So you have to make a compromise between this and that. Okay? So if you make the corresponding, take into account all these, you can say that through issues or the false current issues, then we are getting a curve, you can say that, like this. But through an internal fault case, the point may be with below this also. That is some of the faults will be there, not, you can say that. So the point here is that if you take this philosophy also, what is the percentage of winding we are able to protect? That you have to say 95%, 98%, 99%. If I take this curve to be lower and lower, this boundary lower and lower, like in the overcurrent principle, we say unnecessary trippings will be more and more. Even for the any switching, even in the external thing also, the transformer trip. So therefore, you have to make a balance between the security and dependability, or unnecessary tripping and necessary tripping in between these two. Now coming to this, the other conditions we like to do is two conditions. I operating should be greater than, in this region, In this region, these are all secondary currents or through currents, and so we'll define what is that, how this Irish staining is taken care. So this Irish staining current will be more and more, as we see from earlier, you can say that it should be more and more. So we take a slope here. So any current, because at this point, the corresponding any point happens to be there beyond this curve is an internal fault issue, and the relay should make a trip command for that one. Below this is not an internal fault, either through fault or something. So it ensures that this is not a fault situation. This is the general philosophy of percentage biased differential relay. What is that percentage bias? This is about the biasing now. Earlier you are simply telling, you can say that what? No, simply a threshold, cross it, trip it. Differential relay. But here we talk about now, no, that does not stand to consider whole good because of the CT saturation, CT mismatch, tape changing transformer issue. So we require a characteristic like this, which performance will be better. Performance means discrimination of internal versus external fault. So in this case, we make a slope. And this bias factor is about the restraining part. Percentage biased differential relay. We have explained differential relay before. Biased, that restraining, a biasing factor. More restraint is more restraint we are providing. If you go, we can say that the through current more and more. That is about the biasing. Percentage is slope. M. This slope M is expressed in percentage. 0.1, 0.1, 10%, 0.2, 20%. Now question is, if I see that, should I go for higher slope, lower slope? Should I go for higher slope or lower slope? So this slope is, let us say, you can say that 0.1. Sorry, this slope is 0.1. This is 0.1. Another can be 0.2 if I go for slope higher. So should I opt for 0.1 or 0.2? So if I go for 0.2, many you can say that external events which were earlier taken care as if in an internal fault will not be taken care. Fine, we are extending this area, but many internal faults also will not be identified. If I take smaller m slope, smaller m, then I am, you can say that in problem of having you can say that smaller m, then I am a problem of, you can say that unnecessary tripping is only more and more. So that's the, we have to make a judgment in terms of that. So we'll see what kind of typical values are taken care to address in a transformer or so.
Sir?
Yes, tell.
Sir, in the graph, we see that like after some time, like the graph has started to increase after a particular value of restraining current. So how to determine that restraining current value? Like up to which it will be constant and then it will start increasing the like eye operating curve.
I'll come to that. How do you specify for the in a relay, and so we will come to that. What are the different things? This is not the end. We'll have more to consider that. I'm coming to that. Good questions. That is very much required in the setting perspective also, how to set this relay and all these things. So this is the same, you can say that pictures which we are discussing into that. So we say that I operating is nothing but this. We may say magnitude now, I1 plus I2. And the I staining is what? It is a measure of current flowing through the zone of protection. That the zone means, I told you, between these two cities, zone of protection. This provides the desirable feature of restraining the relay when higher levels of current are flowing. Why do you provide? Because you see here, for any external faults, CT saturation, Masimoth, and so, because of this, the corresponding things were very high. So if you do like this, and during the restraining, during the large amount of current in the external case, the restraining should be more as you adjust from this earlier curve. So therefore, it is not a horizontal line, it is having a slope. So more restraint, more opposition, more bias if the through current is more and more. Through current means secondary current, you can think about in this case. So the restraining current, you can say, which is being universally generally taken care, is calculated like this. Out of this, any one, I restraining equals to some factor of k, I1s minus I2s. If this is difference current, this is added current. Note. This is differential current, so-called difference 5 minus 3. 5 minus 3. Then this is 5 plus 3. Okay? plus minus. I'm changing the sign. So now you can say that either you can do that, or you can add, you can say the magnitude summation of these two, or you can take the max of I1 and I2x also. What do you mean by max of this? Max means if the fault current, if the through current happens to be there, this or this max, or this plus this, as we say here, or in case of internal fault, only this will be there. So that will be max of this, max means this, not this. But for external fault, sorry, for external fault, we'll have, you can say that in terms of, yes, for external fault, we'll have both this and this will be there. So the corresponding max means you can say it will be, these are all normalized things. Yeah? The currents are normalized. We'll come to that, what is normalization also in per unit kind of thing. We think about that, so that there is no confusion between settings, this perspective and so. So what we like to say that the iris chaining, different country, different utility take either this or that. This K factor can be 0.5 or 0.1 depending upon the utility. Anything you can take here, not anything, 0.5 or 0.1, that is a utility take in terms of that. These, all these consider flexibility, who will be watching what, because in numerical this is available. So this is what we talk about, what is iris chaining and this. And as I say, consider the percentage bias differential leg characteristic, what should be. So finally, we say that adding all these issues, we say that a core will be like this. Already we have discussed. So this is the pulse current, which may cheat the relay, even though these are all external business. It is not internal fault. So therefore, you should take a core which is above this one. And this curve can be a nonlinear curve and can be a linear curve. So earlier we are discussing about only one slope. Now we can discuss about multiple slopes also. So this is the tricky thing you can consider in terms of this perspective. So what we say here is that this M1 and M2, there are two slopes. You can take more, and in many manufacturers, they also provide, you can say that multiple the curve also, nonlinear curve also. So why nonlinear curve? This is to suitability, you can say that to this one. Now the questions, as we are asking earlier also, that why should we consider that have a not only M1, why do M2? This is very interesting question. Now what happens when the city saturates, any of the city, let us say saturates, then this saturation means if it is a deep saturation, high saturation, due to very large current, severe fault also, external fault, not internal. Then in that case, what will happen is that the corresponding current in that side will be substantially low. Substantially low. Let us say you think about like this. So CT, this side CT and this side CT. So for external fault, and this CT2 and CT1. So let us say CT1 saturates severely. So what will happen? CT2 will be there. Sometimes many manufacturers can say that take also iris chaining to be considered only I2 also. So whatever it may be. Now which will be the maximum current? Because this has saturated, maximum current will be I2 side, this side. So restraining current will be there. So that becomes towards the right. True, but this is an external fault. So now what will happen? The differential current will be significantly high, because this plus this, that differential current will be so high. So therefore what will happen that in case of the corresponding external fault case, the differential current becomes more high as compared to in this region. And this is the portion where we talk about the more city saturation region. And that's why this corresponding exponential growth here, if you see here, this is about the city saturation curve. Agree? So this city saturation is really a challenging thing in case of this transformer differential perspective. Otherwise, differential is very optimal protection kind of thing, very best form of protection. So to avoid that, we can say that we take not one slope for high level of current, we take another, we can say slope. This M2 slope is greater than the M1, much higher, 0.9, 0.7, 0.8 as compared to M1, 0.3, 0.4, 0.5 kind of thing. So how to set this dual slope? That was the earlier question also. So we have M1, M2, M3. So there are 3 zones now. This is section 1, section 2, section 3 in the characteristic curve. I restraining. So this is I can say I1 magnitude plus I2 magnitude divided by 2 or so we can take or in terms of that, and then or you can say that we can take maximum of these and so also. Fine. Now this is about a differential current I1 plus I2. So these are phasor sum plus I2 and so magnitude of this. Now up to this is section 1, section 2 and section 3. So this is about this starting point is peak of current, peak of circuit. So typically this is 20%, 0.2 or 0.25, 0.2 to 0.3 of rated normal current. Normal current. Rated current, I can say it rated current. Nominal current we call it. Nominal current also or the rated current. Of what? The transformer. So why this 0.2, 0.3? As I say, this is restraining current 0 means no external current. No external current, no internal. This is very small in this region. So what will happen? You can say this is nothing but the magnetizing current, CT ratio mismatch. Even there is no transformer current. No transformer current. Why this you can say is showing? Because this side you can say magnetizing current will flow. Agree? And then you can say that magnetizing, in addition to that, because CT ratio has there is mismatch and so there may be chance of you can say that in terms of field current. So we have to take into this. Many smaller things may happen. Those things can be taken into this one. So we'll discuss you can say that about how to have this section 1, section 2, section 3 in typical things. So that depends upon the choice of the designer or your different relay manufacturers provide different you can say that regions and so. But what the sole purpose is that the internal fault of the transformer must have a trip decision. Okay? So where this you can say that this point, starting point of this, where will be the starting point of this? Typically, let you can say that I say this is 0.5 per unit or non-rated current. This is 1.5 per unit current, like that. Not necessarily this. These are the things also you can say in terms of that. So depending upon the manufacturer settings and in terms of that. So we talk normalized current because of comparison is there. So we cannot compare current of this side and that side because in transformer we have, we can say that different levels of current. So what we say here that three things in the processing of the current. We are talking about a 3-phase transformer, and in a numerical relay, what are the steps to be followed? Different kind of issues. Like I can tell you. So we know that we have a star, grounded, and a delta transformer. Okay. Typically in distribution system we have delta 11 kV side, star grounded, 11 kV side also, and like that we can have. So now these are the things. So what we see here, these transformer being protected. So this is the transformer side. The CTs are connected to the line side. You understand? CTs are connected to the line side. What is line side? In the transformer, inside we will not put the CT. We are putting everything outside. So therefore, these are connected to the line side. Transmission line, distribution line to which it is being connected. Now what happens? Whenever there is a fault happens to be there and so in this section also. So line to ground fault. So through this you can say that ground current will flow. But this corresponding zero sequence current will be circulating here. In the line side, it will not flow. That we know. So therefore, this CT set of CTs which are measuring the current here, this side it will consider the zero sequence current or the ground current. This side it will not notice that zero sequence current and so. So therefore, when you talk about the line side, the corresponding zero sequence current, you can say that zero sequence current in the star grounded side it will be there, not in the delta connected side. So this additional current in this side must be subtracted from the system. Otherwise, again, there will be spill current in the differential protection arrangement and so. So like that, you can say that issues are there in terms of that. So to address in terms of that. So what are the steps we will elaborate in terms of that. So this is, you can say that star grounded, delta, star grounded, delta, star grounded, and this is delta side. W1 and 2, these kind of combinations will be generally very common in terms of that. So this is city group 1, this is city group 2. In the older version of the relay, electromagnetic relays, and so if you read material also, that the star grounded system, the cities were connected in delta, and in the delta side, you can say that cities were connected in star. The reason, because this current here, if you remember, you can say that the current in this side, these currents are we are measuring. Agree? These three currents, line side current. The current in this side, this is delta side current, this is star side current. So they have a difference. Phase A here. But these two phases are because of the star delta connection, star not star star. Because of the star delta connection, we have a phase difference. So if you have a phase difference and taking that phasor, that the corresponding current to the differential current, then there will be always a current. So the phase has to be compensated. So what is it do that delta side should be connected in star, the cities, and star side you can say that the corresponding delta. Then overall you are compensating, and if you take the corresponding delta connection there, and from this side star connection this, in individual phase, we can have a phase compensation. Okay. Now, in that case, you can say that we are avoiding this. But in numerical, we don't require this. Then not done. Blindly, you can say that connect both sides star grounded cities. These are the philosophy. So what you do, you can say in that case, because these are all, once we have this corresponding signal into the numerical platform, only calculations. You can do on all sorts of calculation as you require. So what we see here is that we see that the corresponding perspective that we normalize it at this scaling factor. What normalization? Rated current. We deduct the corresponding zero sequence current if it is there. From this side, we again normalize, that is divide in terms of this rated current and divide by this rated current. This side rating of the winding. We also subtract the corresponding zero sequence from here blindly. If it is now on the delta side, there is no zero sequence current, so forget about that. Now we talk about a vector adaptation. What is vector adaptation? That phase compensation. Why phase compensation? If the corresponding transform is star delta, then because these are connected in city in secondary star grounded, there is advantages also why city should not be connected in delta and so, but still you can say that in terms of that, blindly connect star delta and then we get the vector adaptation. What is that vector adaptation? So these are the different steps you can say that we do, and then after that you can say that you make the comparison differential. This is the differential branch where the corresponding this side phase current, this side phase current be added. How do adding? Again, we compute the phasors. Remember, 1 cycle DFT. In the last, you can say that class we talk about 1 cycle DFT to compute the corresponding phasors. So this corresponding here, the corresponding data are being there, and the phasor you can say that are being computed and so. Or I'm saying that at this normalization state also you can compute and do the normalization. I think here you can do better. We can say that is data acquisition, normalize phasor computation, normalizations, zero sequence eliminations, and then the differential current. Once we have the differential current, then we check that whether the differential current is differential characteristic here, not current, rather differential characteristic, whether the corresponding restraining current versus the operating current, the point is above the trip region or not below it. If it is below it, restrain or don't allow block. If it is above this, you can say that you make a trip decision. That is the philosophy we do in terms of that. So these are the different steps to be there. So the vector iteration, you can say that we have a mathematical formulations matrix there. You can see the literature book also materials are provided. You can see that in this, or you can see the YouTube and all these things. This is nothing but a matrix multiplication in terms of the cos. You can see that term and so 30 degree k factor k. You can say that depending upon this, you can say that the type of transformer. Type of transform is it YD5, YD1, and so this k, you can say these are called the k, you can say that some constant here. Accordingly, you can say that a matrix being done, very generic matrix, and that matrix you can say that you multiply here, you can say that you can compute the phase in terms of that. So this is the relay does. Only have to enter that what type of transformer it is. Fine. Coming into our experimental perspective and so. So we have we have this setup here. As I say, this is the relay. These are the transformer set of transformers here kept here, and then we have this corresponding load here. Some of the loads here also to while to load to increase the through current. And these are, you can say that some to for the arrangement of the differential current, and so we'll talk about that how to do that. These rheostars are have to consider in terms of that and so. And these are some switches you can set to energize the load and the corresponding things. We have auto transformer here to regulate the voltage input to them so that the corresponding currents are being taken care in terms of that. We'll see, you can say that what are the things to be done. So this is that relay part, and we have these connections to the relay, and this is the transformer part. Okay, 110 to 20 bank of transformer, and so this is the load in the 110 volt side, and then from the supply you can say that we have a circuit breaker, and this is the set of CTs here and a set of CTs here. Three phase CTs, CT1, CT2, CT3, CT1, CT2, CT3, and these are connected to the, you can say that relay side here, this side here to 20 volt side. This is so-called supply side, and this you can say that is the load side. You connect here, and the rest you can say that the relay business. Agree? Now, for this you can say that arrangement, what we say that we'll need certain settings and so. So what are the settings? So setting for the dual slope percentage by this. The question you can say that earlier was that what are this? How to set this in terms of this? So the and as far in this you can say that standard relay you can say that MICOM 634 P634. So this IP is 22.2 of this you can say that means 20% of the rated current. If the rated current is 100 ampere and the corresponding time, so it is 20 ampere, 20, 25, 30 you can say depending upon this one. I restraining M2, this is I restraining M2, this is 1.5, this is 1.5. Agree? So I operating is greater than IPU, this current IPU, in the range of this to this. What? 0 to 0.5 pu. So this is up to 0.5 pu, 0.5 pu, this side. I operating is greater than M1 RS, this region is up to 0.5 to 1.5. This is 1.5, 0.5 to 1.5, and beyond that this is M2. Beyond that this is M2. Agree? So there you can see that corresponding things are there. Now the manufacturer has provided you can change M1, M2 flexibly. You can change the M1, M2 flexibly. Generally, manufacturers they fix the corresponding settings in terms of this because of their own internal calculation perspective and so and so. And all these you can say that setting perspective and all these things you can see this reference here also, page 3.132 also you can say that what are the things to be there also. So in these characteristics, this is our trip characteristic, these are block characteristics, and we have to see different values of M1, M2, and this. So this is the characteristics we are talking about. We have fixed some M1 and M2 means this is the characteristics. So what will our target in this one for verification? No. Am I getting this characteristic or not? How will verify this? So what we did here, that how to verify this? This is the transformer. Let's say I'm single phase I'm putting. We have loads and we have supply here. This is 220 volt side and this is 110 volt side. We have CT connection this side, CT connection this side. So for internal fault, if we put the transformer fault, we have 86%, 50% taps are there, and so we can create fault through that also. So what we did here, because we want to verify the characteristics of the one, so we need several points, you can say that, around this. Now, how to get this? We put a resistance here. Those are the resistances I showed. You can see that 2 resistances, double tube and single. So multiple resistances are there. So you can regulate this current through this one. Now tell me, you can say that this resistance which I am talking about, I am connecting here. So this current, you can say that will be there, and this current will be there. So both are in this direction. The point here that this is internal or external. Because it is between these two CT, so this is internal fault situation. So this is, we are emulating an internal fault, you can say, situation to this. And now you can say that anything external, you put, you can say that more resistance and control and make a short circuit kind of thing also, lower and lower, you can say that. Then the corresponding, these are nothing but external to this one. So this, beyond these two cities external, inside these two cities internal business. So what will happen? This, if we reduce the corresponding resistance here, internal fault current becomes more. And as per our arrangement from the very beginning, I told you that we make the CT connection such that during normal condition, the differential current is 0. Okay? That is the polarity connection we do. Now, once you start increasing this, decreasing the resistance of this one, this internal fault current becomes more. So differential current should be proportional to that. So differential current should be more. Agree? So in this characteristic, what you do now is that if we reduce this resistance, then this current becomes more. So this current also becomes more. So I1 plus I2 magnitude will be more and more. So we are going to the right of this one. Once again, in the experimental things, if we decrease the impedance this path, then this current becomes more. Proportional to this current will also flow, this current becomes more. So both I2 and I21 magnitude will be more. So restraining current will be more. I1 magnitude plus I2 magnitude. Proportional to that restraining current. So we are going towards the right. Now, if you, let us say at this point we are here on the restraining perspective, and you like to consider test the corresponding characteristics, what do you want? What do you do that? You go on increasing this corresponding fault current, internal fault current. That is what the operating current will also increase. Operating current means differential current branch. So what do they go on reducing the resistance from a set value, and then we see that we go on increasing and increasing the differential current, and at this point if it reach, then it will trip. Agree? So I set on x-axis about the corresponding restraining current point here. I go on decreasing this resistance here. That is, I am increasing the internal fault current. So therefore, the differential current, I operating current goes on increasing, and in this process, you can say that I find a point when the relay trips. So for a given setting of M1 and M2, the relay trips at this point. So like this, I will find, you can say that different points on this kind of adjustment, and then I will get to consider the corresponding operating the restraining current versus operating current characteristics. So I'll get to consider points like this, and then see that yes, the relay is following the given characteristic or not. That I can verify. This is what we are verifying in this, you can say that experiment like this. But I already told this relay which is available in this one is a for the high voltage application. So the corresponding transformer which we have is very small rating, and so there is some ratio mismatch issue, and so the data set which we have kept here, you can say, is for a larger transformer in terms of that, but that is incompatible with this 220 kV, and this other side is 110 kV. So we see here 220 volt is to 110. Only that we are talking about this is 220 is to 110 kV. So we scale it up because of this compatibility use of the transformer. This is high voltage application relay, but in a downscale manner, we can see that in the laboratory we are using like this. So only that the transformer ratings are mentioned like this, and then the CT ratios are also in accordance with that. And then the corresponding rating of this current, you can say that high voltage side and low voltage side, 125 250 because this is transformer of 110 to 20 sides. So these are the corresponding rating in terms of the 47.7. And once we have this, you can say that. So we have this I operating equals to this plus this, and I is 10 equals to, we have taken this one 0.5, that is K is 0.5, I high voltage minus this. If this is plus, this will be minus. Now we'll come to that verification of that to consider that later on. But on the top of that, there are some other issues in the differential protection. What are the issues? I told you that this is a transformer, and we have our CTs connected, and these CTs are connected to for a consider relay here. Fine. So I switch on the transformer, I energize this. So when I switch on, we know inrush current will flow. What kind of inrush current? This is that inrush current. So in one or two phases, the corresponding current may be significantly higher, 5 times, 7 times, 8 times than the rated current. So where it will flow? When it is no load or light load condition, then if you energize the transformer, current will flow in the primary, not the magnetizing current. The magnetizing current is, as you specify, it's 2%, 3%. No, we are not talking about that. This is current in the primary, in the energization side will flow, which is having substantially high, 5 times, 7 times of the rated current. So what will happen, because this flow you can say in the so-called primary side, and then you can say that there is no current in the secondary side or lightly load condition, negligible, small current. So therefore differential current will be significant. All these currents in this current will flow to the differential branch. So relay you can say that I operating becomes significantly high. So want to say the characteristic cause which we talk about here, in that situation, even it is not a fault, it is an energization. Anytime you can energize for a only transformer, it is not a fault. And the corresponding current you can say subsides of its own after 10, 15, 20 cycles depending on the time constant. So this is not a fault situation. So the relay should not trip. But the point happens to be here only, which is above the trip characteristic, inside the trip characteristic, on this beyond this line, upper portion of the line. So the relay will trip. So this has to be blocked. So therefore, we characterize this, you can say that this one, this, and if you see, you can say that this is the x-axis. So this is having a lot of second harmonic and other harmonic components. So if you go for the FFT analysis, this is of the same transformer energization in the lab. These are collected in the lab to the oscilloscope, and during certain instances of switching on, same 1 kVA transformer, and it goes, you can say that 75 fundamental. How will you go to FFT analysis? So I2 by this fundamental I1, second harmonic versus the fundamental, this goes 75%, high content of, you can say, second harmonic component, fourth harmonic, fifth harmonic, and so. So in general, you can say that transformer, the differential relay, numerical relay, they detect the second harmonic component with respect to the fundamental. And if this ratio is greater than typically in one setting 17%, then they declare that this is not a fault, the inrush situation. So there are other methods also. So this is, you can say that one simple way of, you can say that classifying the signal internal fault, because it falls on the percentage accuracy above 1, so it will detect as a property fault point, internal fault. So even this point is found out, it is not declared as internal fault. Before that, you have to discriminate whether its second harmonic component is significant or not, like this. Then only it goes for the trip decision. This is one check. The second check is about overfluxing. Another point happens to be there that suppose it is not loaded or lightly loaded condition, and suddenly the transformer can say that this side voltage goes high during night condition, light loaded condition or so. If the voltage becomes very high, then the corresponding current overfluxing flux issue, then the corresponding overfluxing issue, the current becomes significantly high, much higher than the normal current. Where it will flow? One side only. So differential current again becomes high. So therefore, again you consider on the percentage bias, you consider it will be above this one. That's the problem. So therefore, to avoid, you can say that on that perspective and see, this must go to restraint. So on the same transformer, you can say that if we analyze this curve, you see here fifth harmonic component. This is about the fifth harmonic component is significant. So I fifth divided by I1. If you notice earlier we talked about I2 by I1, second harmonic to upon fundamental. I fifth upon I1. If this is significant, 30%, 35%, then we declare this is not a fault. This is overfluxing. So these are classification of signals: internal fault versus overfluxing, internal faults versus inrush. So those are the considered things pointing. So what we say that earlier you are discussing about the relay settings, and we talk about this is our arrangement, and we now can say we would like to verify the corresponding characteristic in terms of that. So what will verify? So one case, experiment case. So we took M1 equals to 0.5, much higher, M2 equals to 0.9, and the corresponding threshold setting is 0.2. These are the settings we have to do in the lab, in the relay. So in our measurements, external measurements, not the relay measurements, there are two measurements. One, the relay measures through the CTs and whatever data we have given, and the other one you can say measurements in the current, emitter, and so we can say providing. So we talk about the load current here, and we talk about the fault current here. Fault means fault path current, internal fault. Okay? So these are the currents, you can say that, and we see here the internal fault we are going on increasing. Load current, you can say that on the secondary side also increasing also, and like that. Different sets. So what we see that the restraining current we calculate from here, that this is about the relay data as observed the relay, what the relay provides. Relay also measures, and they're also providing. We'll have to read. I'll show you can say in the next slide. So the relay data, what it takes, that is our concern. This is what I can say check from our external things, emitter, monitor, but how the relay rates, because as I say, the relay cities and the corresponding transform ratings are provided in this data sheet. Where? This. Because this our transform is very small transform, not compatible to this relay. So with that given thing, the corresponding relay and consider observer data. So our analysis will be based on only this part, what the relay sees. So if the relay sees this current, is it following properly? Is it the trip decisions are correct or not? That we like to see for this case. So this you can say that you are talking about. So what you are verifying? Always you are verifying for the internal fault. For internal fault, it should trip or not trip. Now how will find this is nothing but trip and this is nothing but block. So as I already mentioned, I'm repeating that for any can say that corresponding iris training, I go on inching the differential current, and if it trips there, then this is the point I mark. So these are the corresponding points. You can say that star points if you see here are nothing but my observation point. Which are the observations point? And these are the observations point. This setup, this. So I plotted. You can say that this relay observe you can say points here and see. And what we have fixed? M1, M2, 1, 2. So if I do that plotting, you can say that on a plot, this, and this. This is about M1, M1, M2, and this you can say that 0.2. So with this line, characteristic line, then I plotted, you can say that this data, and then see that this is this. So some mismatch happens to be here in this region also. And I told CT saturation, so many other factors. We can analyze state also. It's not in this region is very good at. In this region, it is still to consider reactivity. It's not the problem of the relay. It may be problem of the CT also. CT is not able to faithfully produce in terms of that. So therefore, we are going. It should trip here, but we are going more current. So there are the issues in terms of that. Fine. So I have differential and restraining current in the relay. So that's you can say that during one instant of time, I like to show you can say that how the relay can say that. So this is about the relay data on the relay screen available for an internal fault case. High voltage side, it is showing this is the timing, main current in IA, primary A side phase A current, 60 ampere. LV side also, it is showing 60 ampere because the CT ratio properly shifted, and so both sides can set current there. But this is an internal fault case. So if you see this, you can say that In this case, the operating current will be I operating equal to this minus this. So this will be 0.24 ampere differential current. Agree? So then these are magnitude we are talking about. Phase we have not considered here because we are not able to see the corresponding phase information from the relay. If you see this relay here, this is showing 0.239 I reference because these are normalized currents. So this 0.24 and 0.239 they are close by. So our calculated things and the relay what is showing is in agreement. Agree? Relay is showing this 60-60 at the load side, primary input current and the output current, and accordingly calculating the differential current to be 0.239, which we are not noting in the table. So therefore, our calculation here shows
Sir?
24. Yes.
Sir, this 60 ampere current is the like current on the primary of the main transformer or the current transformers, like this 60
This is
ampere
60
current.
and this is 60 at that time. And this is what the relay is showing at a given instant of time.
Okay, like we are dividing it by the rated currents to normalize it, right? To
Yes,
like
yes. So that finally this you can say that is nothing but the characteristics which you are talking about, restraining current and the differential current the relay provides. These are the sets we are noting from this. And we have tabulated them. So at a given situation, what the relay sees, how much current the restraining current and differential current, this is about the restraining current. Restraining current, consider if this is minus, this will be plus. So the restraining current will be 0.36. Here it is showing 0.359. 0.359. So our calculation shows that this. So when you have, we can say that 60 ampere here in this one, and after this normalization and all these things, the corresponding you can say that differential current and the restraining current should be like this. This for an internal fault. Okay? So like this, you can say all the data are being provided in terms of that. You can see here. The another case you can say that earlier, so you can say 0.5, 0.7. So M1 I maintain, but I maintain you can say that the corresponding this side slope I have reduced. And if I go by this, so this M2 slope is now reduced. Go by this, and I again take you can say that sets like this. So I'm getting all these you can say that points here, and I verify that you can say that this is the reference call. This is my reference call, like we talk about in the worker and relay experiment, and these are we can say that observations point. So I plot like this. So they are close by. It means that how accurate you can say that how faithfully it is going, you can make a judgment. You can account this corresponding mismatch to different regions, including city situation and so city issue and so, because it is very depends on this city also. Okay? So everything is available in this util link also in the NPTEL materials also. You can go like this. So that is what in overall in the experimental perspective on this I would say arrangement of the transformer protections which we talk about here in this setup in the relay lab. So transformers, this is about that I told you that internal fault creation, this part, and for loading perspective and all these things, these two are there. This below also we have a gang rheostat and all these things in 3-phase. These two can say that goes for the combined, you can say goes for the loading part, and this is the internal fault. Combination of these two are in the series, so the tubes are there, so that you can say that you can internal fault can be increased or decreased depending upon this. So we go on increasing the restraining current, means through current, and then accordingly for a given through current, how much you can say that is required, the minimum current you can say that in the external current, a minimum internal fault current is required. That is nothing but the characteristic point issue. Above that, it will trip. That is the point of minimum internal fault current we require for this. So we go from higher resistance to low resistance and see that how the corresponding points are being there. So from here or a point here, set here and go on this, and wherever it crosses, put that point, star point there. So those are the verification of the characteristic. So this is that reference one, and we got different star points here as mentioned, and then we plot them, and then we comment that whether the relay is following the corresponding characteristics set by the manufacturer or not. If it is not following, then we ensure that this relay will be repaired, checked, verified, software, this and that. It is following. You allow them. Now the other option, what you say here, how much M1, M2 and all these things will go, as I showed. If the M1 becomes smaller, then the slope will be this. If M2 becomes smaller, then this will be this. So I can go by this curve also, or I can go by the higher curve also. And this is nothing but the dependability and security issue. In this case, lower curve, many trips will be there, even though some overloading also. And in this case, you can say that those things will be overcome, but many internal faults may not be detected. That is the only issue in terms of selection of higher M1, M2 or lower M1, M2. This is all this perspective. So we have some report submission issue, and this will be supplied. So plot the percentage by differential characteristic for the two data sets that will be provided. Agree, will be circulated. Plot the reference characteristic for the mentioned set also, that M1, M2 that I told you how to do that. So we take it at 0.5 to 1.5. This in this range M1, and then you consider 1.5 onwards it is M2. Okay, and below that horizontal line, as you see here. But that write your suggestions how the transform differential observes the presence of second and third parameter. See, wonder you consider this such a situation indicates the high loading industry. This you can do. For the following set of data table with the fault situation internal external, the relay settings could be, and there you can say this. So we fill up this one 1, 2, 3 justification of this thing. So what you say is that this is a set of data, and you have to calculate the corresponding fault or fault internal or external. You have to adjust from these data sets whether it is internal or external, and these are the three cases: case 1, case 2, case 3. Which is internal, which is external. And the connection you can say that it's as usual. This is the connection, city connection perspective. So based on these phasors, you can say that we can find out internal, external, and then you can justify, consider some remarks you can go. The other one, we have a Simulink model. Kuldeep is there, I think he will demo you. So we have different, this is the transformer. We have F1, F2, different conditions you can say that we have. So there are three cases you can say that in terms of that. So you can connect them in terms of that, and you can do three classes of situations. One is that external fault situation, one is for internal fault situation, and the F1 here you can say that for the inrush situation. And then from there we'll take some certain observations, and from that observations you can say that we'll tabulate, you can say something. We'll provide the table, you can say that what are the things to be filled up and so. What are the things to be there? Create the phase to ground fault F1, F2 at least last digit of roll number. Write your, you can say that analysis for the fault situations. The last like roll number last digit will be used for example the RF value which will be in this question. Yes. Any question, anything is welcome. In the meantime, Kuldeep, can I finish my presentation? Can you demo, Kuldeep?
Yes, sir. Yes, sir. I can show
Okay.
them.
I can leave. You can say that. Fine.
Okay.
Yeah. Stop.
Sir, my screen is visible.
Yes, please.
Just hold, sir.
So these are indicators. If you see the right-hand screen, some digital displays are there. So that display shows you were like in the overcurrent link, the corresponding current and so.
So sir, here this is a 4 buses are there here, and here this is the source, and we connected a breaker here to switch on and switch off the circuit. Then this is a line, half a kilometer line. Then a transformer is connected. Here we are taking measurements here, and that is going to the relay. This is the relay, and here also we are taking the measurement on both sides of this transformer. Then another line is there, then here load is connected. So in this relay here, this is the primary side current, means this side measured current. This is the magnitude. and this will give the secondary side current, this side current. Here operating current will be displayed, what you saw in the equation, and this will display the restraining current, and this display will show you the whether it is an internal fault or not. One indicates a case of internal fault, 0 indicates it's not a case of internal fault. Here it will show whether it is a case of inrush or not. So if it is I will show you. uh, let's run it, and this breaker we have, initially it is open and it switches at 0.1 second. So let me run here.
Kuldeep, we have to connect it. No?
No, let me first show the inrush case, then we'll connect here in 3 different places.
Switch on the, no? This is switching on.
Yes, this is switching on means inrush. This is a case of inrush, and as the differential current in this case.
Kuldeep, please clarify where we have switched on the source.
Here.
Not close the breaker, no? Have you closed the breaker?
Yes, sir. Actually, it is not showing.
Can you show that point 1? So at point 1, it will be switched on. That is what you see.
Yes, sir. This is the switching time. All 3 phases will be switched on at 0.1 second.
Okay, fine.
So here, this is a case of inrush, and as the differential current is high, so it detected as internal fault also. But as the inrush status is 1, the tripping is blocked. So it will not. The tripping will.
See,
Yes.
friends, as I mentioned, whenever inrush happens to be there, differential current will be high. So it will above the trip characteristic. So unless you block it, it will trip. But now it is showing inrush situation after differential current is high. It is inrush situation, so therefore the relay will block it. So if both it is 1-1, then relay will go for a block 1. So whenever there is whenever the internal fault switching 1, at that time the inrush must be 0 to make a trip decision. Proceed. Kuldeep, second case.
Yes, sir. Internal fault.
Now the system is connected to the grid, to the system, to the
The
grid
fault.
side.
Yeah.
So
Yes,
now,
sir. We will.
now all of you see here, it is the sensors are B2 and B3. Is it not? So,
Yes, sir. Yes, sir.
So measurements are from B2 to B3, B2 and B3 for the transformer. So this, when he is connecting these corresponding connections to create the fault, it is in between B2 and B3. So it is internal. So it is an internal fault issue. And when it will be external? When it is beyond B2 or beyond B3.
Yes, sir.
Right of B3 and left of B2. Yes.
Yes, sir. So
internal case now.
Yes.
Okay.
Yes.
So this here 1, 0, no inrush, 1, it implies this. See here the corresponding current also in the which side is what? Can you read the Kuldeep currents?
Sir, primary side it is 3.662. I can zoom in. And this secondary side it is 0.07308.
So you see here the secondary current is so-called secondary current is negligible because we have created fault in the this side internal. So our right hand side current will be negligible because load cannot get the voltage becomes 0 in that phase. So that's the issue here. So clear. So therefore, in this case, differential current will be significant, and that's why it is showing an inrush internal fault situation 1. Okay. Now you can show the third
external.
Yes. Okay, so see here, this fault is beyond the corresponding two sensors B2 and B3. B2 and B3 are the measurement points, like our CT connection and so. So it is beyond this, you can say it means it is an external fault. Now fully will run. So you see here 0, 0, and but the currents are increasing. Okay.
Yeah, it showed ingress,
Ah,
and but it is not internal fault. Here restraining current also increased.
How much is the restraining and how much is this one?
Sir, restraining current is 3.649. Let me start from here. B2 current is 3.662. Here B3 secondary side current is 3.637, almost same.
Both are similar.
Nearly same. Then operating current is 0.025. These all are in per unit values. Then restraining current is 3.649. Nearly half of these two.
Okay.
Half of these two, primary and secondary. Then internal fault, it shows 0, means it is not a case of internal fault. Inrus, it showed it as an inrus condition.
Yes.
So it also supported that the tripping should be blocked.
Actually, in this case, you can say that they no need to compute the inrus because this is not going to the differential things.
Okay, sir.
So friends, this is not there, but this is not a foolproof concept things. But for your clarity and observations how things goes, that is on understanding perspective. So this inrus current which is there, the relay may not consider calculate here. It may calculate, but that cannot be considered in the decision process because it has not gone to consider differential current. It is below the considered characteristics because both the restraining current and the differential current are, you see here at par, the corresponding to currents are at par. So it is below the trip characteristic, so they no need to consider on the inrus. If that point becomes beyond the curve, then only you consider the inrus situation. So this I, the last I, the one here, it becomes redundant, not required. So these are the things to be there. Kuldeep now show how they will vary the RF.
Here, when they open it, this fault resistance on here they can vary. Here you can keep one or
like consider that your what you say in the last class also, like you are varying the last digit of your roll number, you can vary like this and put this.
Yes,
one.
sir.
So
For
here so what are the things they have to tabulate that will mention about these currents and the corresponding status, internal, external fault, and so and so. Agree? So these are the three fault situations, three situations for the transformer. One is inrus. Can you just close this dialog box? Yes. So you see here the fault, you can see that three things. And in my slide I show you, it will be provided F1, F2, F3, three cases. One is inrus, the other is internal, and the other is external. So this is just have a feeling that how the corresponding relay works. So in the block you have fundamental economic estimations. All these things are there. Like if someone likes to incorporate, we can incorporate also overfluxing by I5 by I1 and so, and like that you can include better and better things in the system. And so this is a rough, we can say that idea about how differential protection is being applied to the transformer. So in overall, what you discuss in this today's this lecture is that transformer needs protection, good protection, reliable protection, and that is not fuse is not adequate, overcurrent relay is not adequate, differential form is pretty powerful, but differential, simpler differential, where the differential branch of current becomes high, that is also not adequate. We require percentage biased differential protection, but this biasing is provided by the restraining current, that is through current perspective. I1 and I2 becomes very high for an external fault case, and therefore you can say that the restraint becomes more and more. Now with this CT saturation creates problem, so that's why your slope of towards the right of the curve, you can say that becomes more M2, and M2 should be greater than M1 in general in terms of that. And we verify the corresponding transformer, you can say that characteristic in terms of that. What we did, you can see that in the experimental things, we fix for a restraining current, judging the transformer, step changing transformer, the auto transformer, you can see the voltage and the external load condition. And then we can see that we change the corresponding internal fault resistance path, that resistance, and go on increasing the corresponding current through that branch, so that fault current increases and it trips the corresponding, the relay goes for the trip decision. So that minimum differential current for which it trips, that is nothing but our point of observations which we like to note. So with this, from our side is finished. Any question, any query is welcome. So this will be also submitted like next week before this time, and then we'll go consider to the directional and the distance relay in the relay perspective, the third experiment. Thank you from our side. Any query, any question, welcome. All materials and details are will be provided in the slides. Kuldeep will upload everything. Okay, Kuldeep, Abhishek, we'll close this session then. Thank you all.
Okay, sir.
Yes.
Kuldeep, remind something. Kuldeep, Abhishek, please remind.
Okay, sir.
Can we leave?
Yeah, you can leave. Class is
Yeah,
over.
you may leave. Yeah? If you have any question, welcome. Otherwise, you may leave. So this recording you are doing, Kuldeep?
Yes, sir. Yes, sir. It is being recorded.
You can save the recording. Further things may not record.
Okay.
Close the recording.
Okay.
Stop recording and